welcome to the course Advanced Reaction Engineering. So, in this course today we will discuss about the steady state non isothermal reactor design, and for that particular reactors energy balance equations. So, that we will discuss. So, in non isothermal reactor most of the reactions that is carried out industrially, that is not isothermally, that reactions not carried out. Therefore, the heat effect in the chemical reactor is needed. So, we need the energy balance and how to use to solve the reactor design problems. So, energy balance is applied to the design of the adiabatic reactors. Okay. So, now CSTR reactors with the heat effects and CSTR reactors with the multiple steady state algorithm that we will discuss basically in this course or in this particular chapters we will discuss. Let us say suppose you have a reactions, let us say A is going to be that reactions may be exothermic, endothermic, whatever. So, if the reaction is exothermic, so reactions if we operate inside of the reactor adiabatically, means there is neither heat would be supplied to the systems or we have to will not be taken out any energy or heat from the system. So, once the reactor systems is ready, then we will charge the reactant inside of the reactors and we will maintain the reaction temperatures, that desired temperature is required. Once the reaction has started, then reactions will proceed as per the reactions. Okay. So, for that particular type of reactions, if you conduct any reactions in a adiabatic reactor, so then or adiabatic way, so then what would be the volume necessary for a particular conversion, that conversion may be 50%, 60%, 70%, that we have to find out. At the same times the temperatures that will increase with the conversions down the length of the reactors. So, once the reaction has started, if it is exothermic reactions, once the progress of the reactions will take place, means conversion gradually increase, then since the reaction is in exothermic reactions, then the heat evolution should be theirs, means temperature along the length of the reactors, if it is packed bed let us say reactor, so then gradually increase along the conversions. So, in our previous studies we have discussed that mole balance equations or design equations for a plug flow type of reactor. So, dx by dv design equations we have discussed this, rate equations is this. Okay. So, rate equals to let us say reaction is first order reactions, we can write minus R equals to K into Ca, and this is the concentration and conversion how they are related, and molar flow rate equals to concentration and into volumetric flow rate. So, these are the components we know, and reactions rate constant how they are related with the temperature, that part we know. So, if we substitute K here, concentration here and molar flow rate is here in the design equations, and this R A equals to here. So, then after combining all these three components, so then we will get in the left hand side dx by dv equals to in the right hand side K components and other component that is remains. So, this if we simplify, so then dx by dv, that is the changes of the means conversions along the length of the reactors, we length or volumes of the reactors is like this. So, the nature would be like this. Okay. So, this is the relationships of volume and conversions relationships. So, apart from these also this is material balance or mole balance equation or material balance equation for the reactions. So, with the material balance there is another important task, that is the energy balance. Okay. So, whenever we conduct any reactions inside of a reactors with the material balance, energy balance is also equally important. So, once this part also we have to include with the for the design of a particular reactor. So, then means once conversions is progress, means along the length this way if you notice. So, if we change the reactors volume along this direction, the conversions is also gradually changes along this way for a particular reactions. Okay. So, once the conversion is gradually increased inside of the reactors, and reactors we are operating adiabatically. So, we are if there is any extra heat developed inside of the reactors, we are not taking out. So, under that condition, so what would be the effect of the temperature along the length of the reactor? So, that is along the length or volumes of the reactors, the temperature is changes like this. So, with the conversions also inside of the reactor, temperature also will change. Okay. So, So, this is temperature volume. So, this is temperature and conversions. So, this would be the energy balance line. So, if this is the energy balance equations, so that how that equation has come we have not discussed yet. These are the things we will discuss, means how to develop this energy balance. This is energy balance equations for non isothermal reactor design. So, how that equation has come, this is the let us say inlet temperature of the feed, that feed entering, and at any times when conversion is x, then that would be the temperature. So, at any times let us say this at this particular conversions, let us say 0.60% conversion, then at that times what would be the temperatures. So, using these equations we can find out if heat of reactions for that particular reactions, if you know heat capacity is known and feed at what temperature feed is entering inside of the reactor, and once the reactions is occurring adiabatically inside of the reactors, then at any times what would be the temperature, means at a particular conversions let us say 0.1, 0.3, 0.5. So, at that particular when conversion is let us say 10%, then what would be the temperatures. If conversion is 30%, then what would be the temperature. If conversion is 50%, then what would be the temperature inside of the reactors. That would give actually this temperature and conversions relationships from the energy balance equations. Okay. And from the material balance equations we will get this material balance, and this is from energy balance. Okay. So, these are the things, this energy balance curve or the lines how we can draw, that we will discuss that equations. Okay. So, before that if we discuss about the energy balance, so there are various type of system, closed systems, open systems, adiabatically system, that we should know. So, in the closed systems no mass in, no mass out from the system boundary, but only change in the total energy. Energy may transfer from inside to outside or outside to inside, that is the closed systems. So, energy balance or energy means change in the energy, how we can write dE equals to dQ, that is the heat flow to the systems by work done by the system. So, when we supply any energy to any systems or heat is flowing inside of a systems, for that that systems will means return some work. So, that is the work done by the system. So, if you subtract that part, the amount of the energy heat flow to the systems work done by the system, that is difference is the total amount of the energy that is supplied to the system, or that is the change in the energy. Okay. So, this is a systems is given here. So, this is let us say systems, here Q amount of the energy supplied, and this is the flow rate, means that is the means component A, let us say at a molar flow rate that is entering, with that some component that is present inside of the flow lines, it has some energy that is in terms of the enthalpy HA naught we can express for FA naught, and here when it is the reactant is passing through these reactors, reactions will take place and Q amount of energy we are supplying, and here WS, that is the amount or work done by the systems is this much, and when after reactions that product mixtures that is coming out from the systems, that is the molar flow rate is FA, and with that some amount of energy remain there, that is the enthalpy of component A from the outlet or at point 2, and this is point 1. You can see this way if we consider a system flow system. Okay. So, then for a continuous flow systems for species 1 means component 1, so let us say here A to B, that is the one component forming another component. So, like that in the reactions this is 2 component reactions, like that n number of components may be there. So, n number component may be in, n number component may be going out from the systems. So, when systems is working or flow systems. Okay. So, for first we will consider species 1, then multiple component we will consider and do the energy balance of that system. So, for species 1's rate of accumulations of the energy within the system, that is equals to rate of flow of heat to the system from the surroundings minus rate of work done by the systems on the surroundings plus rate of energy added to the systems by the mass flow into the system minus rate of energy leaving systems by mass flow out of the systems. This is the energy balance, means this is the systems, here this is mass in, mass out, with that energy in, energy out, this amount of the energy supplied, and this is work done by the systems, and here is the flow is there, means when the systems is entering from here to here, there is some pressure drops is or pressure difference is there. So, flow energy is also there, so that also you have to consider. So, then if you write this energy balance in terms of dE system by dt, that is the changes of the energy in the systems per unit times, that is equals to Q minus W, that is the work done by the system, that is the heat flow in the system, Q in, system in, this is the in, this is in, okay, and this is molar flow rate with that energy in minus the energy out, okay. This is energy out from the system, that is energy in, this is energy in, this is work done by the system. So, work done by the systems and this is the out, okay, and that is the energy balance for a systems, okay. So, now for n number of species are present, in that case only here we are changing that much amount of the energy supplied, work done by the systems is this W. So, here this W that worked, this is the flow work plus shaft work, both the works are there, means here this is the shaft, this shaft is work, at the same time flow is there, system that components are present inside of the reactor, that is flowing from the left hand side to the right hand side, that is the called flow work, that is due to the pressure drop inside of the systems, we have to consider that. So, here this is the flow work is this, okay, for n number of species present, and this is the shaft work, that is the total work by the systems done, okay, means flow is there as well as shaft is working. So, two works we have to consider. So, that would be the total work for the system. So, here the flow work equals to minus I equals to 1 to I equals to n, that is Fi, that is the molar flow rate, this is the pressure, this is the volumetric volume is that particular component present, and this is the out, this is in, this is out. So, here's that component we have to substitute here. So, then these equations we can write this way, okay. So, these equations we are writing means just W that we are expressing in terms of this pressure energy plus shaft work, W equals to this, okay. So, now we are this energy and pressure energy that would be there. So, we can write this way, means after substituting W here, this equation after rearranging, so we can write this way, okay. So, here this EI is the UI, that is the internal energy plus other energy, that may be kinetic energy, potential energy, these are the energies is there. So, if we neglect these are the components, so then only EI, that is equals to UI, okay. So, EI equals to UI, that we can substitute here also, then the equations would become this, means internal energy, the energy we are expressing in terms of internal energy by neglecting other terms of energy, okay. So, HI equals to UI plus PVI. So, UI is the internal energy, PVI is the flow energy. So, internal energy plus flow energy, that would be the total enthalpy of the systems, that is in for component ith component. So, if there are nth number of component present, means flowing from left hand side to the right hand side. So, all components you have to sum up the energy, then that would be the total energy, okay. So, then these equations, if UI plus PVI, if we substitute in terms of enthalpy or H, then these equations we can write this way, okay. So, D is system energy changes per unit times equals to Q minus Ws, that is the shaft work, and this work plus and this work minus this amount of the energy. So, at steady state, this system is unsteady state operations. So, when it is the steady state, then the system's energy changes ds part, this part would be the 0. So, then we can write these equations in this form at steady state, okay. So, here Fi equals to molar flow rate, Hi is the enthalpy, and Fi Hi multiply, that is the energy, joule per second, okay, molar flow energy. So, now let us say consider any reactions, okay. So, this is the energy balance at steady state, this is energy balance at unsteady state. So, steady state energy balance, here Q W shaft work and this work energy is there. So, this energy, flow energy, molar flow energy we have to consider for the energy balance. So, now let us say any reactions is this, here two components are in the left hand side, that is component A and component B, in the right hand side are the component B, C and D, that is the product. So, nth number of flow ins. So, in these equations this is the in, this is the out part, okay, energy in, energy out. So, this energy flow in, this part we can write based on this component, all components, this component B, component C, component D, component I. If any inert component is also present when in the reactor, that is here, let us say water is there with A and B. So, water is the inert, A is the reactant, B is the reactant. So, water is also leaving from the systems at inert materials with C plus D. Okay, so, all component you have to consider in the summations I equals to 1 to n, there are 4 components, component A, B, C, D and I, 5 components are there. So, similarly flow out, the energy out from the systems, that is FAH, FBH, FCH, FDHD, FIHI. So, for all components also this is out and this is in. So, now we have discussed in your previous class at the beginning. So, molar flow rate, how we can express Fi equals to Fi 0 into theta I nu I into x, that way we have expressed. This is the stoichiometric coefficient and theta I, that is the molar flow rate ratio. Okay. So, that we have discussed in your previous lectures or last lectures also. So, similarly for component A, if I equals to A, I equals to B, I equals to C, that way you can write. So, if I equals to A, then F equals to this, if I equals to B, then FB equals to this, if I equals to C, FC equals to this, in I equals to D, then FD equals to D and Fi equals to this. This way we can express the molar flow rate in terms of the conversions and molar flow rate ratio, and this is the stoichiometric coefficient also ratio that we can write this. So, now these are the components we can substitute here, Fa we can substitute here, Fb we can substitute here, Fc we can substitute here, for all components we can substitute here. Okay. So, now the differences in the energy balance equation, this is the difference, this difference how we can express, means after substituting all components and rearranging we can get this. Okay. These are the two way we are expressing. Okay. So, here Fa naught and rest of the components, that is the difference Hi minus Hi 0 minus Hi, that is the output input enthalpy, this is output enthalpy. Okay, for individual component I equals to maybe A, B, C, D, I. Okay. So, this way. So, then these components we can write this way, and right hand side these components we can write this is equals to this. Okay. And Fa naught into x is this. So, here this is the heat of reactions at temperature T, that is equals to delta H Rx T equals to this. Enthalpy changes for component D, C, B and A. If we know individual component enthalpy at that particular temperature for this particular reaction, then the changes of enthalpy at that particular temperature T would be delta Rhx, that is the for reactions at this particular temperature would be this. So, if we know stoichiometric coefficient small a, small b, this is the stoichiometric coefficient for this particular reactions, that is the numerical value, maybe 1, 2, 3, anywhere any numbers. So, and corresponding individual component enthalpy at that particular temperature, for to conduct these reactions at the temperatures, the changes of enthalpy we know. So, now if we substitute this component as this, and these are the rest of the component as this. So, then the steady state energy balance equations that we have discussed, these equations, equation 1, there we are substituting all components. So, then we will get equation 2 from equation 1, after substituting these are the components, these are the two components we are substituting, then we are getting this. Okay. So, equation 2 is the energy balance equation, steady state energy balance equation, this is the energy balance equation at steady state. Okay. So, now calculation of the enthalpy changes at temperature, specified temperature means standard temperature to specified temperature if we want to calculate. So, then how the enthalpy changes for component I or component A. So, if we know standard temperature, Tr is the standard temperature, at that particular temperature Hi0 is given for a component, and this temperature, and at what temperature we want to calculate the enthalpy means for a component, let us say A, Tr at this particular temperature Hr is given. If we want to know the Hr for this particular component A at temperature T. So, then how we can find out at this particular temperature enthalpy is this, and at this particular temperature what would be the enthalpy. So, for these equations we have to use, that is due to the change of the temperature for that particular component, what would be the change of enthalpy. Okay, the change of enthalpy we can write Hi minus H0 means for components this way, this is for Hi, this is Hi0, this is Tr to T, this is Tr to Ti0. Okay. So, then we can rearrange this part would be eliminates, and then we can write Hi minus Hi0, that is the Cpi into T minus Ti0. So, inlet initial temperatures and at specified temperature for component A if we know, and Cpi, that is the heat capacity. If we know heat capacity, how we can define for a particular component particular specified times, if we know alpha, beta and gamma value for a particular component A, and that specified temperature we want to calculate the specific heat, using these equations we can find out. Okay. So, now this is our energy balance equations. In energy balance equations, this Cpi T minus Ti0 we are substituting here. Okay. Rest of the part remains as it is. So, once we substitute that part, so then energy balance equation should be this part we are substituting. Okay. So, here Hi minus Hi0 was there, this part we are substituting here in this equation 2, rest of the components remain as it is. Okay. So, then the equations in terms of heat capacity of individual components, this is the changes of molar flow rates. Okay. For individual components, if there is one component, then only consider component A, that is the one. If multiple components are there, so all component individual components this Cp value, and this is the temperature changes we have to consider. Okay. So, now here's heat of reactions at particular temperatures, how we can express this. This is heat of reactions at a specified temperatures, we can write means this is the T temperature, that is the reaction temperature. When the reactions let us say we have a reactant at a particular temperature 298 degrees Kelvin temperature or 25 degrees centigrade, any reactants we have, if we charge inside of the reactor that component, that changes of enthalpy would be there. So, standard temperature that is the Tr is the standard temperature, let us say Tr that is equals to 298 Kelvin or 25 degrees centigrade. So, for a particular component the enthalpy is given. So, if we want to find out enthalpy at 300 degrees centigrade, T equals to 300 degrees centigrade, T equals to 295 kelvins is given. If we want to find out 573 Kelvin of that same components, then heat of reactions this is the delta H Rx0 at Tr, and this is the heat capacity changes, and T minus Tr, this from this temperature you have to find out, and then heat of reaction changes for this particular reaction. Cp delta Cp is the changes for this particular reactions. We have the reactions here, this is our reactions for this particular reactions, this is the changes of the heat capacity, and this is the changes of standard heat of reactions for this particular component. Okay. This is by definition, this is the enthalpy of product minus enthalpy of reactants, that is the changes of initial or standard enthalpy changes, and this is the heat capacity changes product minus reactants. Okay. So, then these are the components, if you know you can substitute here in this term. Okay. So, in equation 3 we are substituting this part. Okay. So, then the steady state energy balance equations will come this. Okay. Q minus Ws minus F A naught I equals to 1 to n theta I Cpi T minus Ti0 minus delta H Rx0 into Tr plus delta Cp T minus Tr into F naught into x equals to 0. At steady state, this is the final energy balance equations. Okay. So, they are shaft work, heat supplied to the system, this is the general energy balance equations. Okay. So, now if we neglect the shaft work, so at the beginnings we have taken that there is means work done by the systems, that also we have considered, shaft work also we have considered. So, if we consider that there is no shaft work, then this part we can eliminate. Okay. So, then these equations we can write this way, equation 5 we can write after eliminating this part, we can write this way, equation 6. Okay. Now, means in general's energy balance we have discussed, this is if we do not consider shaft work, then equation 6 would be the final equation for steady state energy balance equations. Okay. For any system, these equations very important, and these equations we can apply to any reactions. Okay. Any reactions or any systems, these equations, this is the general energy balance equations, Okay. These equations we can apply to any reactions. Now, let us say consider a adiabatic operation is there, the reactions that we are considering A plus B going to C plus D. Okay, this is our reactions. So, in these reactions, if we want to find out or we will to consider the energy balance for this particular system. So, these reactions we have to consider in a adiabatic reactor, means adiabatic operations, not isothermals, means there is no heat supply or heat taken out from the systems when these reactions will take place inside of the reactor. So, everything is insulated outside of the reactors. Let us say this is our reactor. So, here A plus B is going to C plus D. This part is insulated part, means there is no heat in, no heat out from the systems. So, here we conduct the reactions adiabatically, means just at temperature is required we maintain, and then we stop any in or out of the temperature, the systems will work at adiabatics, and then these equations how we can write. So, this is the general energy balance equations. Here this Q part would be 0, W shaft work also 0 for adiabatic operation, there is no shaft work, there is no heat supply in or out from the systems. So, just reactions will take place, then what would be the energy balance in under adiabatic operations, that we want to know. Okay. So, then this part would be 0. So, then equation 6 for this particular reactions we want to going to conduct the reactions adiabatic mode. Okay. So, then the equation 6 after putting Q equals to 0, Ws equals to 0, then after rearranging equation 6 we can get equation 7. Equation 6 and 7 both are same, but only after putting Q equals to 0, no heat supply, since operation is adiabatic, then these equations we can rearrange, and left hand side we can put x, that is the conversions, and right hand side, that is the Cpi, heat capacity of all components. This is the at temperature, this is the Ti, that is the inlet temperature or feed temperature at which feed is entering, that may be 25 degrees centigrade we have started. So, feed temperature may be that. So, we can then once reaction has started, what would be the different temperature as reactions is proceed, means once reaction has started, if the reactions is, let us say it is a exothermic reactions, then with increasing conversions the temperature of the systems will also increase if it is exothermic. If it is endothermic reaction, then with progress of the reactions conversions will increase, at the same time the temperatures of the reacting mixture of the systems will down or decrease. Okay. So, this is the energy balance equation. So, how the temperatures and conversions is related to particular systems when it is under adiabatic operations, using these equations we can find out. This is very helpful equations. Okay. So, now if we know this term and these terms for a systems, these terms if we know, heat capacity changes if we know, if most of the cases these terms we usually ignore, if Cp A equals to let us say 10, Cp B equals to let us say 10, then delta Cp equals to Cp B minus Cp A, this is equals to 0. So, if there is no heat capacity changes for components, let us say A is going to B, in that case heat capacity changes is 0. So, then most of the cases, many cases these terms neglect and these terms dominates. this terms is negligible. Or let us say if we plot for any reactors, this is our equations we have derived, this equation 7 from the energy balance equations. If it is adiabatic Q equals to 0, the equation 7 is this. Here if these are the components except T, other component are known, this is known, heat capacity changes known, heat of reaction changes for that particular temperature, that is known, CPI for components known, individual components known, Ti is known. Okay. So, then right hand side only T is there, left hand side X is there. So, if we change temperatures 298 Kelvin to let us say 500 Kelvin, if you want to change 300, 350, 400 like that, if we change T value, then X value will also change accordingly. So, if we plot X versus T this, so then energy balance line, this is energy balance equations, the energy balance lines will like this, means we have started with 298 Kelvin and up to 500 Kelvin. So, if we plot, then the lines would be this. Okay. So, this is the called energy balance lines. Okay, that has come from energy balance equations for a particular reaction. So, if we these are the components are able to know, so then how the conversion and temperature is related or that is affected for a particular system from the energy balance equations under adiabatic operations. So, then this would be the energy balance lines, for that can be applicable to any reactor, plug flow reactor, CST reactor, packed bed reactor, batch reactor. So, this is the general energy balance equations, and from reaction to reactions these are the components would be different. Okay. So, then once these are the components are different, then this nature of this energy balance lines also would be different. Okay. So, now how to find out heat of reactions and heat capacity for a particular reactions that we will discuss. So, let us say this is our reactions and this is the energy balance equations that we have discussed. So, that is left hand side X, right hand side temperature, that way we can express, or this equation same, left hand side temperature, right hand side X, that way we are interchanging, rearranging that. So, now heat of reactions this way you can write, heat capacity also we can write summation of Cp product minus summation of Cp reactant. Okay, reactant product minus reactant should be the delta Cp. Similarly, heat of reactions also this is summation of heat of reactions of product minus heat of reactions of reactants. Okay. So, this is basically this, okay, product minus reactant. So, these are the components are known. So, then heat of reactions if it is known, it is not given. So, let us say for a particular reactions TR, that is the standard temperature or reference temperature is given for component A, B, C. Heat of reactions is given, heat capacity of component A is given. Similarly, for component B is also heat capacity and heat of reactions is given. Component C and D also heat capacity and heat of reactions is given. So, then these we can easily find out by using these equations, and heat capacity changes we can use also these equations. Okay. So, then for this particular reactions, if all component heat of reactions and heat capacity are known, then heat of reaction changes and heat capacity changes, that we can find out. Okay. So, numerical value this way we can find out, or else here we can put here this heat of reactions whatever we have obtained, and delta Cp value we can put here, and temperature T, let us say at 330 kelvins we want to know, Tr reference temperature is given, then heat of reactions we can find out, heat of reactions this way you can find out. Okay. So, or else also these equations also we can use, heat of reactions for a systems also, product minus reactants also, this way also heat of reactions we can find out. Individual component heat of reactions is given at a particular temperature, how to find out means standard reference temperature heat of reactions is given at T temperature, individual components heat of reactions we can find out, then we can sum of means heat of reactions for product minus heat of reactions or reactants. So, this way also heat of reactions at any temperature we can find out. Okay. So, thank you so much. So, today is up to this. So, today what we have learned? We have learned means how to derive the energy balance equations. This is the energy balance equations. This would be the useful in our next means classes or whatever we will discuss. Most of the cases this is the energy balance equations or this is the energy balance equation. This energy balance equations would be very useful. These equations most of the cases will use. Okay. So, you should remember these equations also, x and temperature, how they are related, and see if we know all these tables. So, then energy balance equation or energy balance lines we can draw with the help of these energy balance equations. Okay. So, this is energy balance lines and this is energy balance equations. So, today for non isothermal reactor designs, the for adiabatic operations, for any operations, so how to derive the energy balance equations, so that we have learned. Okay. So, thank you. So, today is up to this, next day other things we will discuss. Thank you.